Hello everyone, my name is Dan Christopher and today I'm going to be presenting on behalf of my co-authors Peter Hansen and Gail Adley. So our paper is titled IllusionVQA, a multi-model benchmark for optimal illusion visual question answering using clip-based patch cross-attention architectures. So let's start with the problem. So optical illusions are carefully designed stimuli that reveal the heuristics and shortcuts in biological and now artificial vision. So on this slide you can see three classic examples, which is checker shadow, Ebbinghaus illusion, and also duck rabbit ambitious figure. So these are not just curiosities, they are probes and they expose a critical gap. State-of-the-art vision language models perform near randomly on them. So zero-shot clip achieves only 22% accuracy, close to a random chance for a four-way multiple choice task. Even GPT-4V only achieves 58.5%, while humans average 91.8%. So why do they fail? Existing models compresses the entire image into a single global embedding, a CLS token, which discards the local spatial evidence that optical illusions rely on. We identified three properties that are necessary for above chance performance: special preference of patch tokens, multi-frequency awareness through blurred and edge-emphasized views, and cross-modal grounding, letting each answer text attend to relevant image regions. Next is the dataset, which we use IllusionVQA comprehension dataset. Contains 435 multiple choice questions, and then after a 6-stage processing pipeline, including perpetual hashing reduplication with a Hamming distance threshold of 2, we retain 363 unique samples split into 70, 15, 15 into training, validation, and test sets. With only 254 training samples, data augmentation is critical. We designed a 16 random pipeline targeting 3 categories: spatial transforms, frequency transforms, and including downscale, upscale to 28 pixels, and edge emphasis and appearance transforms. So by pre-extracting 50 augmented views per image, we create a feature bank of 12,700 vectors, effectively giving us 50 times our training set size for stage 1 head training. Next, I'm going to talk about the 5 benchmark architectures, all built on a clip 3IT B32 backbone via Hugging Face transformers. So M1 is our zero-shot baseline, which gives 21.8%, which is near random, no training at all. M2 adds a linear probe on top of CLS features. With this, we gain 3.6% in accuracy, but F1 macro actually degrades because the probe converges to majority class patterns. And then M3 replaces the linear probe with a 3-layer NLP and fine-tunes the upper VIT layers end-to-end, only 1.8% chance increase. The CLS bottleneck is still the limiting factor. So M4 is critical architectural change. Instead of CLS token, we use all 49 patch tokens and allow each answer text embedding to query them via multi-head cross-intention. This gives us a plus 7.3%. Last is our full model IllusionVQA. It extends M4 with the multi-view encoding across normal, blurred, and edge-emphasized image views, a bottleneck domain adapter. So together, this add another 3.3%, reaching 37.88%. Next is into a deep dive of architecture of IllusionVQA. So the vision backbone is a clip fit B32 for each 224 times 224 input. The VIT produces 49 patch tokens plus 1 CLS token. Each 512 dimensional, we L2 normalize and extract all 49 patch embeddings into matrix of P shape B49 times 512. So for each candidate answer, the clip text encoder produces a 512 dimensional text embedding. So the core operation is A1 is multi-head attention T1PP. Each answer's text embedding acts as a query. The 49 patch tokens are both key and values. This produces a intended representation that highlights the image patches most relevant to each answer. So the final score for each answer is computed by a 2-layer NLP to the 1526 dimensional concentration. So next is our 2-stage training pipeline. So in stage 1, we freeze the clip backbone entirely and pre-extract features for 50 augmented views of each training image. This creates our feature bank of 12,700 vectors. We then train only the classification head up to 300 epochs with 1 cycle LR scheduling and early stopping at patients 30. In stage 2, we warm start from stage 1 weights and unfreeze the upper 6 fit layers for end-to-end fine-tuning. We use a differential learning rate 5 times 10 to the -6 for the backbone and 1 times 10 to the -4 for the head. Mixed precision training and gradient accumulation by a factor of 4 ensures stability with a small batch sizes. At interference time, we combine 2 ensemble strategies. First, 5-fold stratified cross-validation. We average predictions from all 5-fold models. Second, 8-view test time augmentation. Each test image is augmented 8 times and predictions are averaged. TTA alone improves its absolute accuracy by 1 to 3 percentage points. So this is our main result. So as you can see, our IllusionVQA is the highest in accuracy, top to accuracy, MRR, and also F1 macro. So this is the highest score across all 5 metrics and represents a plus 16.1 percentage point improvement over zero shot clip. So the improvements are monotonic from M1 to M5. So as you can see right here, confirming that each proposed component adds independent value. So the MRR of 0.6035 is particularly meaningful. Even when the top 1 prediction is incorrect, M5 ranks the correct answers higher on average than any baseline. This is not a random behavior. The model is meaningfully ordering its predictions. Next is the evaluation curves. So the confusion matrix of M5 shows a clear diagonal pattern with values of 0.37 to 0.41 per class. Contrast this with baselines where entire rows collapse to near zero. M2 literally predicts option D correctly 0% of the time. M5 avoids this by learning a balanced decision boundary. So as you can see, the calibration curves reveal an interesting trade-off. M2 and M3 have nearly perfect calibration, but at the cost of low accuracy. M5 ECE is 0.24, which reflects overconfidence in high probability predictions. So lastly, the training curves for M5 show stable optimization. Train loss decreases smoothly over 15 epochs, with validation closely tracking and no catastrophic overfitting. So lastly is analysis and discussion. So moving from zero shot to a linear probe gives 3.6 accuracy gain and dramatically reduces calibration error. F1 macro degrades them. So from M2 to M3, adding MLP yields only 1.8%. The bottleneck is 512 dimensional CLS factor. And then our strongest finding, which is from M3 to M4, switching from CLS to all 49 patch tokens with cross attention, delivers the largest jump by 7.3 percentage points, which I mentioned earlier. And lastly, from M4 to M5, the final 3.3% comes from multi-view encoding, where views captures global geometry, edge views enhance contours, combined with domain adaptation and contractive loss, giving us a balanced F1 macro of 0.3796. But our test set of 55 example means one wrong prediction shifts accuracy by 1.82%. So, and the gap to human performance remains substantial by 37.88 versus 91.8. Now is the conclusion. We benchmarked 5 clip-based architectures on the IllusionVQA comprehension dataset and demonstrated that spatial patch tokens, not global CLS embeddings, are essential for reasoning and about optical illusions. Our proposed IllusionVQA model achieves 37.88 accuracy, 57.58 top 2, and 0.6035 MRR, an absolute improvement of 16.1 percentage points over zero-shot baseline. The step-by-step ablation step confirms that spatial preservation, multi-frequency awareness, and cross-model grounding are jointly necessary. No single component alone accounts for full improvement. The gap to human performance 37.88 versus 91.8 remains substantial, and we believe this dataset will serve as a valuable benchmark for the community going forward. Thank you for listening to this presentation.